Radar stealth is a hotly debated subject among aviation fans. On this channel we have already covered this subject a few times. What we never did though is going beyond the two main considerations that lead to stealth, that is, specular reflections and radar absorbing materials. So this is your advanced stealth course. Let's get started. Welcome to Millennium 7 Star, the channel that helps you make sense of military history and military technology. Please stay with me till the end, because this time I really couldn't find any other place on YouTube where this subject was covered. Maybe I'm wrong, but I hope you will stay till the end anyway. So let's do a quick recap of the principles of radar stealth, in case you haven't seen the video we have just dedicated to this subject, and the link is in the cards and in the description below. To reduce the detection probability of a radar, what you want to minimize is the power of the reflected signal toward the radar itself. There are two main methodologies to do this. One is radar absorbing materials. They reduce the energy bouncing off the surface that they are covering by simply absorbing part of it. Two is the reduction of the specular reflections toward the emitter, which is normally obtained with the typical shapes that you see on stealth. When we have applied these two principles, we have done already a quite good job, but still there's quite a long way to go. The reason being that, according to the radar equation, the power received is inversely proportional to the fourth power of the distance between the emitter and the target, and directly proportional to the radar cross-section. I remind myself that the radar cross-section is a measure of how good or bad is an aircraft or any other object at reflecting the radar energy. It is a property of the object itself. The lower the radar cross-section, the lower is the energy reflected toward the emitter. If the probability of detection decreases with the fourth power of the distance, it means that even a small reduction in radar cross-sections will do wonders at a long distance. But the flip side is that when you get close to the target, also the probability of interception increases with the fourth power. So if you want to gain the last mile of stealth, that is, if you want to be stealth being quite close to the emitter, then you need a drastic reduction of radar cross-section. Basically, if the detection probability drops quickly with distance, it also rises quickly if you reduce the distance.
Sir, that wasn't very rigorous, sir.
Okay, Otis, do you think you can do better?
I certainly can, sir, but I will not. I have other business to attend, sir.
Great. Specular reflection is typically the largest component of the reflected energy, but there are at least three other effects that produce a radar return: the surface wave return, the creeping wave return, and diffraction. The surface wave happens on a conductive component, like a antenna rod or a metal plate, when it is excited by the impinging radar radiation. The element behaves like a transmission line till a discontinuity is encountered or the wave gets to the edge of the component. In this case, a non-directional radiation is emitted and the wave bounces back toward the other side of the component until the process is repeated. Obviously, at some point, if it's not continuously excited by new radar radiation actually impinging on the plane, obviously the wave will dissipate. The creeping wave happens when the surface wave that we have already seen actually travels along a circular element of the aircraft. For example, one of the panels or the elements composing an external drop tank. While the wave travels around its circular path, it emits radiation in every direction, including the direction where it came from. Another function of the edge that is so characteristic of the front section of stealth aircraft is also to stop the creeping wave from circulating all around the fuselage of the aircraft. Another reason why external stores do compromise stealth is because they are often cylindrical. External fuel tanks, weapons of any kind, they tend to be cylindrical and built with separate cylindrical elements that don't stop the creeping wave from propagating. Diffraction happens at sharp edges and pointy elements like the tip of the radome, the tip of the aerodynamic surfaces, and the leading and the trailing edges. Typically, the radiation is actually scattered in different directions, may not be omnidirectional, but definitely it is scattered on a large solid angle, and it is definitely that you don't want if you want to preserve stealth. This type of scatter normally happens when the wavelength of the impinging radiation is of the same order of magnitude or up to an order of magnitude smaller than the local curvature. Smaller wavelengths have specular reflection. Higher wavelengths are either scattered or just not influenced. Particularly important is the diffraction from the leading and the trailing edge of the wing, because there it happens in a sort of a conical pattern which is named the Keller cone, and the power emitted actually depends on the length of uninterrupted conductive surface that you have on the edge. The longer the uninterrupted conductive surface, the higher is the energy emitted into the Keller cone. We have seen in the previous video that avoiding vertical surfaces in 90 degrees angles greatly reduces the specular reflection. The concept is reflecting the radiation away from the direction where it is coming from, so you need to avoid vertical surfaces, but you need to have flat surfaces, canted tails, and you need to avoid external stores and pylons. However, even if you do this, this is not enough to avoid surface waves, creeping waves, and diffraction. So what can we do for these three? The first reduction measure is designing the plane surfaces, reducing gaps and discontinuities. In practice, this means having panels made of the same materials and having junctions and joints with the same electrical properties of the panels. This is obviously easier said than done. Discontinuities are unavoidable, so something needs to be made to manage them. Fillers made of radar-absorbing materials can be used between the panels. It is actually very visible on the F-35 where there are those gray strips, various points of the plane. Those are additional fillers of radar-absorbing materials. When gaps are necessary and cannot be filled, like for example everywhere you have a hatch, then jagged borders reduce the energy emitted by the panel sides, and they're generally designed in a way to point the Keller cones of the panel in low priority directions. Also, jagged panels do have specular reflection toward low priority directions. This is the reason why all stealth planes have this kind of sawtooth appearance that are their typical look. And also notice that the sawtooth actually reduces the distance that the surface wave can travel, so the Keller cone intensity is actually reduced as well. Leading edges, trailing edges, all the sharp edges, like for example on the intakes, actually cause diffraction. One way of reducing this effect is actually treating the surface, applying a resistive strip where the resistance goes from 0 to a very high level and then reduces again. In this way, there is no abrupt discontinuity of the electrical properties and the traveling wave is actually absorbed. Another methodology, more complex, is to make, for example, the entire leading edge of radar absorbing material and then hiding a metal structure with no discontinuities or with a sawtooth as well under the radar absorbing material, but this is obviously structurally more taxing for the aircraft design. Actually, the two methodologies are often combined, so on the same plane you find the resistive strips and inserts of radar absorbing materials or parts made of radar absorbing materials, depending on the kind of optimization that the designers do. So this is for the airplane structure, but there are parts of the plane like canopies, nozzles, intakes that do require some specific solutions. But this will be the subject of Stealth 103. In the meanwhile, if you haven't done already, you can watch the first part of this series and the other videos that we have published about stealth that are going to appear beside me.
Well done, sir.
Thank you, Otis. Where are you talking to?
I was trying to bond with the TV set in the reception room, but it didn't work, sir.
What do you mean bonding?
She looks great and she has so many lovely pixels, but she is not very interesting. All she talks about are TV programs and YouTube videos. I proposed watching a film together, but she asked me £7.99 for that, sir.
Otis, she's not as smart as you. Well, actually, it is a smart appliance, but it is not like you. Otis, you're unique, you're one of a kind. There's nobody else like you.
Why nobody else is like me? Why am I alone, sir?
Thank you for watching.